Okay, well, we're going to start talking about chemical bonds. What would you call a bond? So in general, like in relationships, what's a bond?
Connection.
It's a connection, right? And in chemistry, a chemical bond. I'm actually going to write on this first slide.
Like when you glue things together for one thing, that's a bond.
Yeah, it's like if you had pieces of wood and you wanted to glue the pieces of wood together and then make a bigger piece of wood, you would bond them together using glue. Okay. In chemistry, it's all about pluses and minuses. Okay. And it's also about satisfying the octet rule. So the octet rule, we kind of mentioned it the last time. What does it mean? Things like to have 8 electrons. So that's why the noble gases, like, all right, neon, have these valence electrons. They have 8. And I'm going to show you this, but this is how you would draw a neon. You would draw it with a 4-dot, it's like a box. You don't see the box. And on each side, you can put 2 dots. And these 2, 4, 6, 8 represent the octet. And those are the s and p orbital electrons in the atom. And it turns out when you can fill that up, it's happy. Okay? So bonds, in theory, make you happy if you're a molecule. Okay? And lots of research has shown in people that's what makes people happy too. So what bonding theories do, okay, is going to help us predict how atoms will get together to form molecules or ionic compounds. And then later, once we have that sort of down, we're going to learn about how molecules are shaped. Like what shape, what structure do molecules actually take? Are they flat? Are they three-dimensional? All those kinds of things. That will all come about once we understand how atoms bond together to form molecules. And the simplest theory is Lewis theory. Okay, so Lewis was a scientist early in the last century. He was curious about how bonds would form, and so I'm going to teach you a little bit about Lewis theory. So let's start with this, though. There's 2 kinds of Lewis structures. We call it a Lewis structure, or we call it a Lewis dot formula. Okay, the 2 kinds that I'm thinking about are the kinds for atoms and the kinds for molecules specifically. And when we do Lewis structures, the really important thing to remember is that we're always going to be dealing with valence electrons. Get my pen to be a pleasant color again. I like that color. Is that an okay color? You don't care, huh? Okay. So the number of valence electrons, right, is what's important. And we know that the valence electrons for any main group, so that's the A's, okay, is group number. So if I go to, for example, nitrogen, right, and say, oh, I want to take a Sharpie and draw all over that, but nitrogen is in group 5A. And you can remember if you just get rid of the 1, right, that's the 5. It's in group 5A, so it has how many valence electrons? 5, right? So that's the thing that's going to be important for us. So this is a little bit of review, sort of some new and some review. So what we're going to do is the electron configuration for oxygen, just again as a review. You guys want to use chord notation? You want to write the whole thing out? We'll write the whole thing out. It doesn't really matter for this one. It's pretty small, right? So we'll go, we're going for oxygen. And so it's 1s2, 2s2, and then where does it end? 2p4, because remember, I did 1s2 because I know everything filled up to here is filled. So I know this is 1s. I know this is 2s. So this is 2p. It's on the second period in the p block. So it's 2p 4. So that is the electron configuration for oxygen. Its valence electrons are how many? 6. It's these guys. But I know that because oxygen is in group 6A. Oops, I drew that weird. If you do, or 6A like that, if you want to get rid of the Roman numerals, but I kind of like the Roman numerals. It makes me sciencier, you know. So this is how we do the Lewis structure for oxygen atoms, not the molecule. So I'm going to put a little note here. This is for the atom. Okay. You draw an O for the oxygen, and you put dots around it. And 1 dot for every valence electron. Now, do you see the order I did that in? I just started on one side, go back through it. I started on one side, and I just...
You didn't show it, though, you did.
Yeah, that was weird.
It would come out strange.
I went like that. I just went in order, clockwise. You don't have to go clockwise. You don't have to start on the right. You don't have to start on the left. That's okay. This is also okay, as long as, as long as I have 6, and you can only put 2 electrons on a side, and you don't pair them up until you have to, okay? So this is an okay way to do it, all right? So is this. It doesn't matter where the dots are, as long as there's 6, and they're unpaired as long as possible, okay? Go ahead.
The number of valence electrons is always going to be the group number that it's in.
Group number for the 6A, 7A. All right. Good? So we're gonna do a whole bunch of them.
How did you know you had to go to the pairs after 4?
Ah,
Otherwise, you could have distributed them 6 right there. See what I'm saying?
I'd love to record this lecture, but it's just not happening. Sit again.
Okay, you went around, you put 4 dots, and then you
Right.
started doubling up.
Right.
How come you knew to start doubling up after 4?
Because there's 4 sides, right? And you have
So it's always 4.
it's always 4. The most you can have undone is 4, because you think about the oxygen being in a box,
Okay.
and you can kind of think about it like this. Oxygen has an S and 3 p orbitals,
Okay.
right? That's 4 orbitals altogether.
Okay.
So the box here, the sides represent the combination of the S and p orbitals, and we like to keep them separate before we pair them up.
That's more. Thank you. That's good.
What's not cool is this thing is real. Our Wi-Fi is really horrible today. Hopefully, it took all that time to get this up here. Let's try drawing on it and see. So we're going to do Lewis dot structures, okay, for these elements, and then we'll work on molecules. Hydrogen, help me. 1 dot. Oh, that didn't work out so good. 1 dot. There we go. Helium. 2. A lot of times they'll draw it separately or together. Helium, because it's a noble gas and doesn't really bond, and it only has the s orbitals, sometimes they just pair them up. But that's okay either way. Lithium, how many? 1. Beryllium? 2. Boron? What group is it in? 3. It might be good to have your periodic tables out, huh?
Wait, doesn't helium have 8?
No, helium doesn't have 8 because it only has s orbitals to deal with. It's in the first period of the periodic table. P orbitals that give us the 8, the octet, only happen from the second period down. Right? It can't have 8.
Okay.
Yeah, 2 total, so that's,
And the lithium is only one because the core, the first orbital.
yeah, the lithium is only 1 because it's in group 1, and the core, the 1s, we're not drawing that. We're just drawing the valence electrons. So carbon is 4, nitrogen. So now we have some choices here, right? We're going to go 1, 2, 3, 4, and then where do you want to put the 5th one? It doesn't matter, okay? Just annoy people. I'm going to put it at the bottom because I think that's not where they want it. And the oxygen would be 1, 2, 3, 4. And then this is where we have to start pairing up, right? So I could choose any 2 and just pair it up. So I could pair here and here if I wanted to, or I could go there and there. It doesn't really matter. Okay. So this is the Lewis dot formula for an element, and we'll do fluorine and neon real quick.
But it pictures what you would do if you had the p orbitals and the s orbitals, and you will fill them.
Yeah, it's kind of a picture form of the S and P orbitals.
And when you start filling them to 2, then you end up doubling them up on this.
So neon looks like this, right?
Cool.
And neon, noble gas. What do we know about noble gases? They don't make charged ions. They don't react with other elements. They do that. Why do they do that? Why don't they do all those things?
They have all the electrons.
Stable.
They have everything they need, right? They're happy. This is the term in chemistry we will use. This term I use all the time. Neon is happy. I used to always say neon is like the Michael Jordan of the elements, and so is argon, because everyone wants to be like Mike. Do you remember those commercials when you guys were probably infants? You probably can watch them on YouTube. Everybody wanted to be like Michael Jordan. Now it would be like LeBron James or something. I don't know what it is. Who's the popular basketball player? Stephen Curry? I don't know. That's what people want to be like, right? So all these other elements want to be like whoever that person is. So we'll get to why that's important in a second, but everything wants to achieve that configuration. Okay, so we're going to talk about ionic bond formation. You could read the slide. I'm not going to read it. What does ionic bond sound like? Metal, non-metal, right? And a bond between 2 ions, so a cation and an anion. So one of the neat things about Lewis structures of atoms and understanding the octet rule is that it helps us to predict what the formulas of compounds will be, okay? So if I take magnesium, what's its Lewis dot look like? 2. So it's got 2 dots. I'm going to do this. And then I'm going to do sulfur. So it's going to have how many? 6. Like that. How many electrons does magnesium have to give away? 2, right? Sulfur needs 2 to make its octet. Now remember, magnesium, if you think about its electron configuration, it ends in, or it's going to be neon, all right, and ends in 3s2. So these 2 electrons are these 2 electrons here. So what ends up happening is sulfur takes those electrons, because of its high electron affinity, right? Magnesium has a low ionization energy. It's easy for those electrons to move over. And so what you end up getting is you end up getting magnesium 2+. And how many dots should the sulfur have now? 8. And its charge will be 2-. And normally we put the anions in brackets. and then indicate the overall charge on the outside. Sometimes they'll put the charge on the inside. It kind of just depends on how they feel on the day, I guess. But you recognize sulfur with its 8 electrons now appears like argon. We say that it's isoelectronic. With argon, because it's filled its valence shell. Its valence shell is its s and p orbital, so you fill this up, it looks just like argon. It's not argon because it has the different nuclear charge. It's a different number of protons. Magnesium, on the other hand, looks like what when you take 2 electrons off? Looks like neon. So, in forming of the compound magnesium sulfide, magnesium loses enough electrons to become like the noble gas neon. Sulfur picks up enough electrons to look like the noble gas argon. Okay, they become isoelectronic with those gases. And that gives it its stability. And that's why when you form the compound magnesium sulfide, it's 1 magnesium with 1 sulfur. Because one has 2 electrons to give, and the other one has 2 to take. Okay, or wants 2 to take. The ionic bond part of this, okay, is the fact that when the electrons essentially are stolen by the sulfur from the magnesium, it forms charged ions. So I have a cation. How do I do this? Cation. And I have an anion. And because of their charges, electrostatic charges, they're attracted to each other. And it's that attraction that's the ionic bond. And ionic bonds can be really strong because charges are usually really strongly attracted to each other. So we don't draw anything in between them. We just know that they like to be together because their charges are opposites of each other. Gonna do one more. We'll do sodium and oxygen. So, how many valence, what's the Lewis dot for sodium? 1 dot. And for oxygen? 6, right? So, how many electrons does oxygen need? 2, right? So, to get to its octet, so it's going to take a second, it's going to take 2 sodiums for that to happen. So, the electron will go there, the electron will go there. And then what you end up with, 2 Na pluses and an O2 minus. And usually, like I said, hang on, let's do the dots per. Like that. Or sometimes they'll do a subscript 2, or sometimes they'll draw the sodiums on either side. Okay, as long as you somehow show it's 2 of these to 1 of those. This is the Lewis formula for an ionic compound. You draw it with brackets and you show the sodium ions separately out. So for example, let me show, this is probably better to show it like this. Like that. But again, that's why the formula takes the form it does, because oxygen needs 2 electrons, sodium has 1 to give, and that's where we get the formulas from.
Would it still be correct to write it as 2Na instead of 2 separate ones like on the exam?
Well, it probably, if you're going to do 1, I was just thinking about that, probably should be like this instead. Yeah, because you put a 2 in front of it. Like, for the 2 to be in front of the sodium, there has to be like a space between the 2. But
Or else it would include the oxygen.
it would include the oxygen
It
otherwise,
makes
yeah.
a compound out of it.
And, yeah. Okay, so any of those variations that I just showed, this one and the one just before it are okay. All right. Okay. That's all the wording. There's some examples. We'll do the Lewis structure for sodium bromide. Now we're just going to write it real quick. Go ahead.
Sorry, going back to the word, you take that plus will make neon?
Yeah. So sodium's here, right? Lose 1 electron. It'll be like neon, And then oxygen is here. It'll also become like neon because it picks up 2 electrons. So they both become isoelectronic with a noble gas, which causes them to stop gaining and losing electrons. And that's what gives us our charges and our formulas. So if you wanted to think about, if you wanted to think about sodium and bromine, right, just to write it rather than think about how all the electrons move, sodium ions Lewis structure is simply Na plus. What's bromide's going to be? It's going to be Br minus, right? So I'll write Br. How many electrons for Br? 7. So Br minus would be 8, right? Yeah, because it's an ionic compound, sodium bromide. Sodium is, got 1 electron. It loses it. Well, that's weird. That dot came from my hand. And then bromine is actually bromide, so it's a -1 charge. So that's going to be -1. So you'll end up getting the 7 for bromine, and then 1 more because of the negative charge, like that. And then the Lewis structure is just like that. Okay. And that negative charge could go either on the inside or the outside. Usually it's on the outside, but I kind of drew it in the wrong place for it to be on the outside, so I just left it there.
So this only happens when there's a metal and a non-metal?
Yeah, so this is just for metal, non-metal. It turns out if it's covalent, like we talked about, remember we did nomenclature with ionic compounds and covalent compound? Metal, non-metal is ionic, so that's how you do all the ionic Lewis structures, and then all the covalents are different, and we'll talk about that. It's done a different way. And that's what we'll focus most of our time on today. Okay, I'm skipping some of this. Okay, so we're going to do the Lewis structure for hydrogen and oxygen. So what's hydrogen? Lewis dot structure for hydrogen. H. And it's got 1 dot. And oxygen is O with 6 dots. So let me ask a question. When we make water, right, and you think about the formula for water, why are there 2 hydrogens with the oxygen? To make the octet for the oxygen. Now the hydrogen's okay with 2 electrons because it's small. Okay? But to make an octet, you're going to need another electron like this. And that's what we get the H2O from. That's where the formula comes from. It's to satisfy this octet rule. So the way this works, okay, let me show this is going to be can be confusing at first. Really confusing if it doesn't draw. Okay. I'm going to draw a circle there. And you look at the circle that surrounds the oxygen and all the electrons on it, right? There's 8 in that circle. That's the octet for oxygen. Now, remember, one of those electrons came from hydrogen. It's not different enough color. Let me group something that's really different. It's not good either.
How about yellow?
Maybe yellow, huh? Bright yellow?
Yeah, bright yellow. No, that's too light.
That's too bright.
Well, it's too close to white.
I know.
There, that's okay.
That's just a horrible color.
Not very good looking.
Somebody vomited on my screen.
Yeah.
Sorry, that's not a nice thing to say about that color. That might be your favorite color, and if it is, I'm sorry. I said that, or I'm sorry it's your color. I'm not sure. So that was that open-ended apology that wasn't an apology. So hydrogen wants to have 2. The reason hydrogen they call it the duet or the rule of 2, and I can't bring myself to say it. It wants to be like helium because that's the noble gas that it's closest to. Okay? So if it picks up 1 electron, it'll be like helium. And if you draw a circle around this, I'm going to switch back to a pretty color. Actually, that's not a bad color. I just like having too much fun. Both of those guys have 2. So these have 2, and these have 8. And so, since everybody is like a noble gas by sharing those electrons, okay, they're happy. That makes sense? They get stability by sharing the right number of electron pairs with their neighboring atoms. Go ahead.
Is that just still for hydrogen? Can I become helium?
Yeah. That's the only one that's 2. So that's why I always have a hard time saying, oh, it's the rule of 2. It could have just been the rule for hydrogen, and it'd be a little bit more, descriptive, right, instead of vague. So, yeah, so it likes to have 2. So, real quickly, another way to draw this is like this. So a line, regardless of where you see it or how it's drawn, is a pair of electrons. It's 2 electrons. And in this context, okay, these are called bonds. They're covalent bonds, though, because they're molecular compounds, and those electrons, in order for us to do this, it implies that they're shared between the hydrogen and oxygen. So this word that we're going to talk about, covalent bonds, okay, literally is co, bonded to valent. So valent means the valence electrons, and co means shared. So covalent bond literally means shared electrons. Now, the sharing doesn't have to be equal. Okay? The sharing can be unequal, but they're still nonetheless sharing. And the reason they share is so that they can get their octets or their duets. Okay, their
Do you mean
twos.
by shared that they go around both of the nucleuses when they share?
Yeah, so when it's shared like this, when you think about how orbitals must be interacting to form a bond, these electrons are literally shared by both atoms. And they're in the orbital that's created by the 2 atoms when they bond. Yeah. And you cannot tell one from the other. So I drew one as puce. I think that's what that color is. And the other one is reddish, whatever that color is. But the atom can't tell the difference. It's just electrons.
Electrons and electrons.
An electron's an electron, yeah. Okay. Gosh, I could say a lot more on there.
Yeah.
So we have bonding pairs. Those are the shared ones, okay? And then we have lone pairs. Those are the ones that are, or non-bonding. Those are the ones that are not shared. Okay, so on my structure for water, now I'm going to draw it this way, because it makes it a little easier to write on. This is what I had. How many lone pairs do you see there? 2 lone pairs. These are the lone pairs. What are they doing? They're paired up in an orbital and they're hanging out. I think that's about the only thing you really say about them. And then there's bonded pairs. How many bonded pairs do you see? 2. That's these guys. Let's do it like this. Kind of like Mickey Mouse. Big ears. Okay. So a lot of times, like it says here, that bonded pairs are shown as lines. Now, one of the things I'll teach you later when we're doing these is when Lewis did these structures, he didn't draw the dots. So this is not a book thing. Lewis would have drawn it like this. Because this is the 2 electrons. And then in the modern day, what people have converted that to, is this. But in any case, right, what I drew on the previous slide is true. A line means 2 electrons. So when you do octets, the reason this is nice for octets, you go 1, 2, 3, 4. It's really easy to see this line that's drawn this way. So that's 1, 2, 3, 4. That's 8 electrons. So if you count lines and multiply by 2, that's the number of electrons that you have. So you can do it any way as far as I'm concerned, but the most standard way is like this. The next most standard way is like this, and this is like the original way. So you can pretend you're Lewis at the beginning of the 1900s and working by light bulb or whatever. Candle. No, I think he had a light bulb by then. I think Edison was long done by then. Okay. So Lewis structures also help us understand something about the diatomic elements. It says here, it explains why halogens form diatomics, but it also explains why oxygen and nitrogen also form diatomics, okay? So watch what happens when I take bromine, and then we'll do some of the other elements. Br2. So I'm going to put 2 bromines to start with. Lewis dot for those is what? 7, right? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, each one needs what? 1, right, to be happy. So if each one takes 1 to be happy, you notice there's 1 here and 1 here. I can bring them together, and I can make a bond there. So Br bonds to Br. And then the dots. Oops, got crazy with my dot there. And then you want to check your octets. Oh, that didn't work. You count that, and you count that. So for the bromine on the right, that's 1, 2, 3, 4 pairs, including the bond there. That's an octet. And then on the one on the left, you can do the same thing, but you see symmetry-wise, it's exactly the same. 1, 2, 3, 4, that's 8. I haven't introduced any electrons or anything. It's just the electrons they have, and now they're happy, and so bromine makes a diatomic as an element. That's why it does that. Now, let's use the same thing and see what happens. It says hydrogen will also be, but I think you can figure that one out. So, yeah, and that's also covalent. Covalent just means the shared valence electrons. Anytime you have 2 nonmetals bonding, it's a covalent bond. And covalent bonds is the defining structural part of molecules. So like when we did nomenclature, we had ionic and molecular, ionic and covalent. Right? That breakdown also breaks down the types of structures they are, whether they're ionic type formulas that we first did, or whether or not they're the covalent ones we're doing now. Most of like the stuff you have to do in drawing structures is covalent. Okay, so it deals with just this part of the periodic table. And the rest of it's just stuff. Okay, oxygen. What's the formula for oxygen? Elemental oxygen. O2 from the periodic table, one of the diatomics, right? So, I'm going to put another oxygen there. And then I'm going to put pairs of electrons on it. I'm going to do a little erasing on this one, but I'm going to do this kind of well, no, I'll just redraw it. How many does each need? 2, right? But they each have 2 unpaired, right? So if you do it like this, you can go like that and like that. And then you take care of the octets for both, okay? So we would draw it like this. And now they're sharing 2 pairs of electrons. So we call that a double bond. Now this, right, that's how many electrons there? 4. So if I draw my circles, and you count, right? 1, 2, 3, 4 pairs. That's 8 electrons. Then do the other one. 1, right? 2, I'm counting pairs. 3, 4 pairs, that's also 8 electrons. So both of them are happy, they have their octet. When oxygen bonds and forms a diatomic molecule, it's going to come out as O2, and it's going to have 2 bonds in between. We refer to that thing like that as a double bond. That's that phrase that's up there. Each oxygen contributing 2 electrons to form the bonds. I always want to do that. All right. So double bonds when 2 pairs of electrons are shared. When you get 3 pairs of electrons shared, what do you think we call it? Triple bond, right? It also explains something. Just cruising along here. Yeah, so just a little bit, some side notes. Double bond, 2 electron pairs, double bonds are shorter and stronger than single bonds. All right? So what does that mean? Shorter and stronger. Why is that? The electrons are like glue, right? And so the more glue you stick between the 2 things, which is not necessarily true of woodwork, but the more glue you stick between 2 things, the more strongly bonded together they will be. But also, that happens because the atoms are attracted to the electrons, and the more attraction you have for the electrons, the closer you will move together. Okay? So my wife likes to refer to our family as a triple bonded family, because we have 6 children. And each child is like an electron, right? So I have 3 pairs of electrons between us. So that's kind of like my wife and I are now triple bonded because we have 6 electrons in between the 2 of us. Although the electrons are bigger than us now. I don't know how that worked out, but. Okay, so just a note, if you have an oxygen-oxygen double bond, it's 121 picometers. It's 10 to the minus 12 meters. That's small, right? In a single bond, it's 148. So that's an indication that if I have a single bond versus a double bond, the double bond will be shorter. Okay? It will also be stronger, and that's the reason why it's shorter. Okay, so nitrogen, N2. These are all the classics, by the way. We kind of have to teach you these. I don't know why, but it explains a lot about nature. Nitrogen likes to form a diatomic, right? So nitrogen has how many valence electrons? 5. Like that. How many does each need? 3. So if you think about it, like if it pairs that one, pairs that one, pairs that one, that works out. So nitrogen, when you find it in nature, it looks like this. It's also really stable. That's why there's so much nitrogen gas unreacted in the air. It just sits there and nothing really reacts with it, except for like lightning and things like that. Which, I guess if you got struck by lightning, you'd probably react too. So, triple bond, 3 pairs of electrons. Again, nitrogen-nitrogen triple bond is 110 picometers, and the bond distance is 100. Double bond distance is 124. So again, triple bonds shorter than double bonds, shorter than single bonds. Now, here's the piece that makes it a little bit confusing. If you're trying to compare nitrogen to oxygen, inherently oxygen is smaller than nitrogen. And so the bond distance changes because the atomic radius changes. So you can't directly compare nitrogen-nitrogen double bonds to nitrogen-oxygen double bonds or oxygen-oxygen double bonds. You have to have some consistency in what you're comparing. You can't do that. But in general, triple bonds are shorter and stronger if you're talking about the same atoms.
These are closer, the atoms are closer together.
Yeah, so here's what we're doing, a bunch of words here. Okay, I'm gonna skip over these and make it very concise. That was like, you saw 3 slides. I'm gonna write it in 4 little phrases, okay? And actually, let me go over here. I'm gonna do it at the bottom of the previous slide. And the details of all the steps are in the previous slides, but the first things that you want to do are draw a skeleton for the structure. And these could both be 1. Add up the valence electrons. And you're gonna, when you draw a skeleton, you're gonna have a central atom for all of these structures. You're gonna have 1 atom that's in the middle of the structure. So bond everything to the central atom once. So, what are bonds made out of? Not a trick question. Huh? Electrons, right? So if you count all the valence electrons up, and you draw a bond in between the atoms to the central atom, you will have used some of those valence electrons up, because the bonds use 2 electrons for every bond, right? So this, you're going to draw a skeleton, you're going to add the valence electrons. It doesn't matter what order you do these in. Sometimes I don't even say draw a skeleton, I just draw the thing, and we start from there. Then you're going to bond everything to the central atom once, and then what you're going to do is you're going to have electrons that are left over. So we call those the remaining electrons. Distribute remaining electrons. A lot of times I just call it RE. And valence electrons are often abbreviated VE. And the last step is satisfy octets. So what does that mean? Well, remember like in nitrogen we have to satisfy octets, so we have to bring pairs of electrons and move them in? That's what it means to satisfy octets, okay? But it's going to be a little bit different, because when we do these problems, we're going to do them in such a way that we don't have unpaired electrons. We always distribute paired electrons. So since we don't have unpaired electrons, we're not going to be moving things together. We're just going to be moving things in, pairs of electrons in. You'll see how this works in a little bit, okay? I'll try to be really clear on these examples, but this is for you guys in the guys in the morning. This is all makes sense. It kind of looks like what we did all morning. In the afternoon, they already did all this. Right? We're going to do it again, so you're going to see it again in the worksheet, and I'll explain it one more time there. Okay, so we are going to do a Lewis structure for CO. This is a simple one. Okay, so the first thing is to draw a skeleton. Now, there is no central atom for this one in a sense, because it's just carbon and oxygen. So we're just going to bond them together. Okay, that's my skeleton. So I'm going to draw this out, and I'm going to actually do it in steps. Okay, so I'm going to go C, this is step 1, C bonded to O. And then step 1 also includes count the valence electrons. How many valence electrons does carbon have, and how many do oxygen have? 4 and 6, so a total of, yeah. So I'm going to do 1 times the carbon plus 1 times the oxygen. That gives me 10, okay? Which looks like some weird math, but that's okay. So I bonded everything to the central atom 1, so I just made a bond. So my thing is I have electrons that are left. How many electrons haven't I distributed? Well, I distributed 2. I haven't distributed 8, yeah? So there's 8 more electrons. So my remaining electrons is 8. So I start with my skeleton that I had before, and then I stick pairs of electrons on. Okay? So you can, however you want to do it. You can go like that. There's 8. Or you could do the old Lewis way. That's like this. And remember, I'm doing it in pairs, so I need 4 lines, right? Are they happy? No. So in order to make them happy, all right, what am I going to do? Well, I have to start sharing. And since I put the electrons out here first, I'm going to have to move some of these lines in between until I make them happy, okay? So let's see, what can I do here? So I'm going to, let's do this. So go C. I got my 10 electrons. 1, 2, 3. And then my carbon and oxygen. So I brought 2 of the lines in. And that could be like these top ones up here. And that means I have 2 lines on either side still. So I'm going to draw those as dots like that. So all I did was said, okay, these aren't happy, right? So they need to share more. And the way you share them is by making double and triple bonds. So when you don't satisfy, you put the electrons around, the octets aren't happy, this is 2, 4, 6, then you need to start sharing more electrons. Now the process, right, sort of went like this. If you do it step by step, I took this pair of electrons and I moved it in here, right? Now you notice what happened when I took, this has how many, this one has how many electrons around it? 6, right? How many does it have now? Still has 6, right? 2, 4, 6. This one has how many? 6. Oh, sorry. Just got to finish it up like this. Now it's got 8. So by sharing that extra pair, like by this guy contributing his electrons over here, right? He caused this guy's numbers to go up, and then I take another one, and I'll take that same one, and I'll move it in. That is, I'll take this guy and move it in here as a line, right? Because a bond is 2 electrons, and a pair of bond is 2 electrons, and we're just drawing them as lines, so this represents 2 electrons, right? So I can just move it in. So when I move it in, it becomes like the structure that's down here. Okay. And then I just didn't draw the lines on either end. I just drew them as dots now. Yeah, lines or dots. And then in the middle here, if you didn't want to draw the lines, right, you would have had 6 dots in between here. It just gets real clunky when you have to have that many dots. So lines turns out to be just a little easier to interpret.
They favor the oxygen?
Yeah, they favor the oxygen because oxygen is further to the right in the periodic table, so it's got a higher electron affinity, and so it tends to, the electrons tend to be more towards the oxygen than the carbon. Okay, we're going to do H2CO3. So now this is where I'm going to give you a rule because we have a central atom. Yeah.
How many covalent bonds do you have?
Oh yeah, so that's a good question. How many covalent bonds can you have? It turns out like carbon can have 4. And for like most of the stuff we commonly encounter in the main group elements, it's 4. Okay. Why can carbon have 4? Because it has 4 unpaired. Like in this Lewis dot, it has 4 dots. So each one can form a bond. Then you can't have more than 4 dots, right? You can't 4 sides, so you can't make more than 4. Okay. It turns out in the transition metals, when you have the d orbitals, so now you're talking about s's, p's, and d orbitals, you can have like 5 bonds or 6 bonds. Okay. But the bonding that occurs in like carbon occurs because of the s and the p orbitals, and there's a total of 4, like 1 s and then 3 p's. That's where the number of bonds comes from. It's limited by that. Okay, so H2CO3, this is formaldehyde. Here's a rule for drawing skeletons, okay? Most unpaired electrons or unique element like there's one.
Yeah, that's,
Okay, this is what goes in the middle. So like SO4 2 minus, you could draw a Lewis structure for that. What do you think goes in the middle? S, yeah. Oh, it was carbon in the carbon. Yeah.
Sorry, I was looking at the actual.
Oh, sorry, yeah. In general, though, right, we're talking about carbon a little bit, about 4 bonds. If you have carbon in a structure, it's usually always in the middle because it can make the most bonds, okay? And in this problem, right, you have H2CO. Well, you have 1 C and 1 O, so that second rule doesn't help you at all. So the C in its Lewis dot looks like this. And the O in its Lewis dot looks like this. So this has 4 unpaired, this has 2 unpaired, so the carbon's in the middle. But in general, when you have a carbon in a structure, stick it in the middle first. That's the best shot that you have at getting it right. So I'm going to put C in the middle. And then I'm going to put the H's and the O on it. And then I'm going to count my valence electrons. So that's my skeleton, okay? Oh, I want to try doing something here. Yeah, whatever. Okay, so how many valence electrons? Well, oxygen has 6, right? Carbon has 4. And there's 2 hydrogens with 1. So that's a total of 12. How many have I used up? 6, okay. So I subtract 6. So this was step 1, right? And then I'm going to calculate 6 remaining electrons. That's what I have left to distribute. And I'm going to distribute them in pairs. Okay, so here's the next thing that I want to tell you, because this just makes life easier. If you don't do it this way, it'll still work, okay? It's just harder. Put the electrons, put electrons on the central atom last. Satisfy the octets or duets of everything else first. And then if you have any left over, stick them on the central atom last, okay? So place remaining electrons on central atom last. So I have 6, right? That's horrible handwriting, sorry. The central atom is which one? Carbon, right? And so hydrogen can take 2 electrons. It already has its 2 because it has a bond. So that means they all have to go on oxygen. So when I put them on oxygen, you're going to go like this. 1, 2, 3, 4, 5, 6. Or like this. 1, 2, 3, like that. Pairs. Okay? Now I'll get my fancy dancy brush out here. Hey, that has an octet. This has 2. This has, yeah, this is 8. This is 2. This is only 6. So in order to make it happy, somebody has to share with him, right? Which way are we going to share? Does carbon have anything to share? So the electrons are going to have to come from the oxygen. Okay. So one of these pairs that I drew up here is going to have to move. One of these ones up here. So I'm going to redraw it down here because that's what you guys probably should do to keep track of things. I have a C, I have an H, I have an H, and then I'm going to bring down a pair of electrons to form a double bond. And then my oxygen. How many electron pairs are still left on the oxygen? 2. So again, you can draw it. I don't care how you draw it. You can do it like that, or you can use dots. I just want you to know how to interpret it, okay? And then when you check for octets, well, the hydrogens are good. All the hydrogens need in life is a bond. And once they have a bond, they're happy, okay? That has 8. And that has 8. So this Lewis structure is done. Okay? Okay. So now we're going to do, and this guys that were in the morning lab, we didn't do these. They're not on the worksheet for some reason. I don't know why. But so pay attention to this part. We're going to do polyatomic ions. So if you're a polyatomic ion, right, you've got like sulfur and oxygen, and you have charge. Why does like sulfate, why does sulfate have a -2 charge?
Need additional electrons to fill the valence.
The reason sulfate has a -2 charge is it needed 2 more electrons to satisfy the octets of the structure. And so that's why it carries a -2 charge. To make it stable, it needed 2 electrons. So here's the thing. For a polyatomic ion, right, you add 1 electron for every negative charge, and you subtract 1 for every positive charge. So you draw out the skeleton, you count the total number of valence electrons, and then you adjust the number of valence electrons according to charge. So if I did sulfate, I would get a number for total valence electrons, but it's a -2 charge, so I'd add 2 to it. For ammonium ion, which is a +1 charge, right, I'd get the total number of electrons, and I would subtract 1 from it. When you're done with the structure, for the Lewis structure, for any ion, any anion really, but any polyatomic ion, you put brackets around it, and you write the charge. Oh, I made it crash. You write the charge in the upper right corner outside the brackets, just like I showed you before. Okay, so let's do Cn minus. So skeleton, C bonded to N. Oops, looks like M. How many valence electrons do I have there? 4 and 5, it's 9. But it's Cn minus, right? So I'm going to add 1 to it. So that's the total number of valence electrons I'll be dealing with. They just happen to have stolen a valence electron from some poor metal ion somewhere. Okay. And then I have 1 used up, so my remaining electrons, I do 10 minus 2, because of the bond I put between the C and the N. So I have 8 left. I did my valence electrons. I counted. Remember, this 1 is for the charge. The remaining electrons, this is for the bond I drew. So I have 8 left. So I'm going to distribute how many? We have 8, so 4 pairs. Okay. So okay, I'm going to go ahead and say this. We'll do it this way. You can distribute them any way you want. Okay, there's actually 2 ways. Yeah, you can distribute them any way you want. I'll just say that. Okay, but since nitrogen has the higher electron affinity of the 2, it actually works out pretty nicely, since it's a diatomic ion, to just put them on the nitrogen first. But you don't have to do that. You could go like this, for example. I'm going to just draw 2 different ways. So I could go like this, and that's 2, 4, 6. So I need 1 more, right? But you notice the nitrogen is full now. It has its 8. So I can do 1 on there. So if you look at the nitrogen, he's real happy. But if you look at the carbon, what is it?
Short.
It's short. It's short by 4. All right? So it needs 2 pairs of electrons to make it happy. So I can redraw this then. Like that. It needed, again, the calculation was here. It's short, 2 pairs of electrons. So I could just take these 2 and move them in between, and then that's what the structure looks like.
And nitrogen still has its 8.
And nitrogen still has its 8, and now carbon has its 8. Now, the more traditional way, and you guys do need to know the more traditional way, but this is, you know, you're going back and honoring Lewis when you do this. The more traditional way to draw that is like that when you're done. Now it's an ion. Brackets, minus 1 charge. But if you'd put them on the carbon first, you could have still figured that out, because what would have happened if I had done this? I would end up with that. Then the nitrogen would have been short too, and you would have stuck them over there. So don't feel like you have to be, oh, I got to go with this one first or that one first. Doesn't usually matter that much. The analogy I gave for this in the lab this morning, it's like frosting a cake, right? You don't get the frosting all right the first time around. Who hasn't frosted a cake? Okay, you should make a cake someday. Frost it and give it to somebody. Don't use the little oven with the light bulb in it, though. That cake is horrible. You guys remember? You guys know what I'm talking about? The little easy bake oven when you're a kid, and you would like put stuff in it, and it was horrible. Don't do that. Anyways, but we all thought it was awesome. Yeah. We even had one when I was a kid that had edible plastic in it. Oh, it was nasty. It was so cool. We made lizards and bugs out of it. Okay. Didn't affect me at all. Yeah, go ahead.
So that would be a triple bond then?
Yes, triple bond.
And they want to do that because even though they would both be satisfying with, because the carbon can have 4,
No. So you're thinking about dots in its Lewis structure for its atom, but in that compound, when it forms a compound, it wants to always have
It wants
eight.
eight.
Wants eight.
So it wouldn't just be satisfied with
This
a
would be like,
bond in the middle,
yeah.
and then two, and then three.
Yeah.
They want eight.
Yeah.
Okay, I can see why, okay.
Would you have this without the ion, then you would still have the same structure?
but you would have, yeah.
You need to carry that negative
Yeah, if you
bond.
didn't do that, right, if you didn't put the -1 in there, the structure you would have ended up with would not have been charged, but it would have been something like this. Or that, actually, probably like this, because the nitrogen's the more wanting of the electron than the carbon is. So you guys, have you ever heard the term free radical?
Yes.
All right, are free radicals good for you or bad for you? Bad. That's an example of a free radical. A radical is the general term for a radical, and you probably should know this, is an odd electron molecule or species, okay? That means it has an unpaired electron somewhere. And it turns out these things are so reactive that as soon as they run into another molecule, they will literally rip an electron out of it and say, I'm happy now and you're not. Right? So your body uses free radicals to kill like foreign invaders in peroxides. You know, like the T cells and all that stuff. You guys know what I'm talking about? Yeah, that's what a radical is, okay? I suppose I could go all kinds of crazy ways. Okay, so now we're going to do what is that? It's not chlorate or not chlorite. It's, what is the name of that dude? Not chlorite, hypochlorite. So we're going to do the structure for hypochlorite. Names. Cl and O. Okay, so how many electrons? 7. And 6. And 1, right? For the charge. So it comes out to be 14. So I'm going to go, so this is my valence electrons. My remaining electrons, I've just drawn 1 bond, so I have 12 left. So that means I have to distribute 6 pairs. So I like doing them in pairs so I can draw lines. So I'm going to go 1, 2, 3, 4, 5, 6. What do you think? It's done. Everybody has an octet, so we're going to draw it as C, L, O, and then dots. But again, I like the lines because they're fast and they're real visible. And so when you do it that way, you don't tend to lose track. Like when you do dots, you lose track of dots because they're small or your pencil doesn't draw it very dark or whatever the case may be. But the lines usually show up. And again, the lines could be like this too. But those tend to get lost with like the L of the CL a lot of times. Like you'll end up with a CL on the right and you'll draw lines around it like this, and then you'll miss like the fact that you have these 2 lines and you think you have carbon with a bond on it, or you get all. So the way Lewis did it originally is probably the best. Okay, so now I'm not done with that yet, right? What do I have to do? Brackets and a minus. Okay? So there are some exceptions to the octet rule. NO, for example, can't satisfy the octet rule because nitrogen has 5, right? Oxygen has 6. That makes for 11 total. You will always have an unpaired electron there, okay? The other real significant exception to the octet rule is things like boron. Boron tends not to satisfy the octet rule because carbon has 4, right? So it makes 4 bonds, but boron only has 3, and so it doesn't usually make 4 bonds easily. It can make 3 bonds because it has the 3 electrons to make bonds with, but a lot of times it ends up being short. So don't be surprised if you see boron in a structure that looks like this or like this, and the octet for boron's not satisfied. That's one of the known exceptions to the octet, just because it doesn't have enough electrons to get there. Okay.
Does
There-
aluminum work the same way?
What's that?
Does aluminum?
Aluminum's the same thing, but illuminates are ions, and so what happens is another oxygen comes in and donates pairs of electrons. We talk about that. That's another conversation. The other common exception is when you have more than 4 things bonded to a central atom. So things like sulfur and phosphorus can sometimes have 5 things bonded to them, but you can still use this way that I showed you how to do the loose structures to get their structures, okay? So remember I said, right, these guys like the octet rule, and that determines the number of bonds because s and p orbitals, right? Once you get down to here, s, 3s, 3p, what else is there on the energy level 3? D orbitals. So that's what these guys actually use. They use d orbitals, a couple of d orbitals, so they can make up to, right, 6 bonds because they can pull in 2 d orbitals. Now, it's not 6 bonds to one thing, right? 6 single bonds. They can do things like that. And phosphorus over here has 5 single bonds, okay? These are known as expanded octets. They're an exception to the octet rule, but based on what our current knowledge is, the octet rule should have these quotations around it saying, hey, you know, there's these other orbitals and you can do more bonds. We just use it to help you when you're starting.
So you know that little square that had the phosphorus, sulfur, arsenic, selenium?
Yeah.
Does that have something to do with that too? You know how they had 1 more oxygen? Those 4 were like an exception. Is it those 4 also for this rule?
I don't know if I can, I don't know if I have a good answer for that. Sulfur and phosphorus with the 4 oxygens don't have to expand the octet. I'll think about it.
Okay.
Yeah, I don't know if I have a good answer for that. It'd be nice if there was a good answer, but I don't have a good one now. Okay, so we're gonna do SO2, okay? When you draw SO2, I decided I like standing here and looking at the screen. Is this weird for me to stand here and look at the screen with you guys? I could stand in the back corner, that would be awkward. Like I could sit next to you and lecture. All right, I can actually, with this, I can pull a chair out. I should start my 1A classes next semester this way. And just start writing on the board. See? Oh, it's freaky. Okay, so what we're going to do is we're going to draw the structure for SO2. So sulfur. Oh yeah, this is just awkward. It is really comfortable though. And 2 oxygens. Oh, I drew, we're really too small too. So I'll go back to my place. Oh, do we need a break? Are we doing okay? What? Let's do like, okay, can you promise me if I say there's a 10-minute break, you'll be back in 10 minutes? I'm talking to you.
Me?
Yeah, because you and your friends over here are always the last ones back. Promise me 10 minutes and we'll take a break.
The 10-minute club.
Yeah, 10 minutes. Ready? Go. 10-minute break.
That's great.
Okay, so we're going to do SO2. So S, there we go. O and O. And how many electrons? 18. Minus, so this is my valence electrons. All right, and then we're going to do remaining electrons. That's going to be 14. So now I can draw my remaining electrons on. I use the lines, right? So I need how many lines? 7, because 14 divided by 2. So go 1, 2, 3, 4, 5, 6, and then 1 goes in the middle. Now remember what I said before, it's easier when you do these if you put the remaining electrons on the non-central atoms first, or do this one last. So that's why I did 6 more on here, 6 more on here, and then I did the last 2 here. So here's the deal. This has an octet, this has an octet, this has 6. Is he happy? No. God, I love how you guys all responded there.
Yeah.
Maybe we should take more breaks. I just did that to taunt you, sorry. So I could double bond on the left side or the right side to do this. So either way, works out, okay? So anytime you can get 2 equally correct Lewis structures or more, right? Like they look equivalent to each other. These look like mirror images. They're actually known as resonance structures. Not renaissance, resonance. Resonance structures, and it turns out that if you measure these bond lengths, like remember we said double bond is shorter than a single bond earlier? Yeah.
For the discount, let's say maybe for the OSL, aren't you missing one more covalent bond on for the S to make it 8?
Here.
On the right side.
Oh, here? Oh, I forgot the little dude up here. Sorry. Yeah. Good call. Okay, so, good? Yeah, okay. So, he's so far in the back, we use semaphore. We have to.
Well, actually, you're missing one on the oxygen on the right, too.
Oh, my. This one?
Yeah.
No, because it's part of this now.
Oh, I got it.
Yeah, it's supposed to be missing.
All right.
It's kind of like some of my parts. So, never mind. My appendix is missing. All right, it's supposed to be missing.
My kid is
Oh, yeah. Yeah, well,
Never done much of a picture.
yeah.
It's subliminal.
Oh, man. Yeah, I had to clarify that appendix thing, right? So here we have, it can be drawn like this or it can be drawn like this. They're known as resonance structures. The real structure is an average of those two. It's like somewhere in between. Now, your book likes to use analogies like this. Oh, well, like this, right? You have this kind of dog and this kind of dog, and they make this kind of dog. That's actually what the structure looks like. It's known as a hybrid of its resonance structures, okay? Or the way I usually think of it is, I'm short, I have dark hair, and my wife is tall and has blonde hair, right? And my kids are all tall but have brown hair and brown eyes. She has blue eyes, right? She's Swedish, I'm Japanese, but our kids are like literally partway in between us. We are the resonance, like mom and dad are the resonance structures, but the kids are the hybrids. They're the in-betweens, okay? They're very good looking, by the way. Just thought I'd point that out. Did you need to know that already or not? Okay, so normally when we draw sulfur dioxide in its Lewis structures, we put this arrow. This arrow in the middle is the resonance structure arrow, this guy here. Okay, so that has to be in between, and then for every resonance structure, you'd put another arrow in another structure, okay? All these bonds, like these ones, like this trick question kind of stuff, right? Which of the bonds in SO2 are shorter, the single bond or the double bond? And the answer is neither, because it's a hybrid. It doesn't actually ever look like this, right? Yeah. But in general, double bonds are shorter than single bonds. But like I said, that's in the trick question realm, right?
Will that be on the test?
Maybe be on the test, maybe not.
That's the trick.
Yeah. So we're gonna do nitrate or nitrite, and include resonance structures. She's tired of them already. Sorry, that's okay. Oh no, I get it. Did you stay up all night last night too?
No, I was in bed by midnight.
What?
Yeah.
That's 3 more hours of sleep than I got. Wait, what time did you get up?
7:45.
Oh, dang, you suck.
It's not too bad.
Okay, no, I got up at 7. So, how many electrons? Yeah, I saw the email. What? How many valence electrons? 18, good. Is that right? 17 plus 1, that's 18 valence electrons. I'm not going to do all the math for you anymore. So, how many remaining electrons? 14 again. You'll notice a lot of these numbers come up over and over and over again in Lewis structures. So I need to distribute 7, right? So what's going to happen? 1, 2, 3, 4, 5, 6, 7. It looks kind of like SO2, but it has a charge. But the Lewis structure will be very similar. Now, is nitrogen happy there in the middle? No. So we got to make a double bond somewhere. So we're going to take a pair of electrons from an oxygen and move it in as a bond. We've already got it drawn as a line so that we're good there. But we're going to go like this. And then we're going to go like this. And then like this. Or we could put an N and go like this and like this. And so those are the 2 resonance structures. Now it's an ion, right? So each one of them needs a bracket and a minus charge. For sure on the test, you should expect to draw a couple of these things, right? Not multiple choice questions. Right? From scratch, draw these things out. Okay. So we're going to be talking about shapes, and we may not get through everything, but if I have to, I'll finish it, because the morning group already got some of the shape stuff, but I want to make sure we all try to get through as much of this as we can. Shapes is based on what we call VSEPR theory. VSEPR theory stands for valence electron, right? Valence shell, electron pair repulsion. And then basically it uses the idea that electrons repel each other to predict shapes of molecules. Okay? Simple as that. So let's explain that. Okay? So CO2. This is the Lewis structure for it. Central atom is carbon. So when we're talking VSEPR theory and we're talking about shapes, we're usually referring to the shape around one atom. Okay? So we're asking, what is the shape of this molecule around this atom? Well, you have 2 groups, right? So if I had 2 children that were trying to run away from me, and I grabbed one with one hand, and I grabbed one with the other, where would I end up probably? If they're running in opposite directions? Go like this, right? Or if they hated each other and they were trying to fight, I would stand in between them, and I will hold them like, I haven't had to do that, thankfully. Hold them apart like this, because they repel each other. I want to keep them as far apart as possible, right? And this is the idea of VSEPR theory. The groups want to be as far apart as possible. So I can pretend to be CO2. Carbon turns out to be a really big atom in the middle. Okay? Here's my oxygens, and here's another oxygen. Right? If they were like this, what do you find around each oxygen atom? Electrons, right? Those electrons repel each other, and they will continue to move apart until you get to this distance, because once I go to this distance like this, what happens? They're repelling from the back. They're closer in the back than they are in the front, so they'll come like this. In fact, the molecule itself, just kind of interesting aside, actually oscillates like this. It's like a spring, and it just goes back and forth as it sits around and absorbs energy from its environment and stuff like that. So this shape, because I have these 2 electron groups, turns out to be linear, and the bond angle is 180 degrees. That's what this little number down here is telling me. Okay? So a linear molecule, there's 2 electron groups, linear geometry. Now, if you had 3 objects and you're trying to keep them far apart from each other, okay? This is that molecule that we did before. This is the formaldehyde. The hydrogens have electrons associated with them. The oxygen has electrons associated with them. So the central atom is this carbon in the middle, okay? The hydrogen and oxygen are trying to get as far apart from each other as possible. So they will take this shape that you're seeing on the bottom right. This is known as a trigonal planar geometry. Because the molecule, when the things are 120 degrees apart, those groups on the sides are as far apart as they can be. Okay? Now it is true that this group is a little bit bigger than these groups are, but for the most part it's going to be about 120 degrees. Because this group is bigger than the hydrogens, it will tend to push them away a little bit. So this top angle, this one up here, in formaldehyde might be a little bit bigger, and this bottom angle might be a little bit smaller. Okay? But what you need to remember, linear is 180, trigonal planar is 120. Okay?
So we don't have to know the angles of the other ones?
Oh, we're getting there.
Yeah.
Okay. So here's the interesting thing, and there's just so much interesting old data on this, I just don't have time to go into it. CH4, right, has 4 groups around a central atom. And if you look at it on paper, it looks like a square. So they say it's not square planar with bond angles of 90 degrees. It's tetrahedral. Now, we did this in the class this morning, but I'll do it with you guys later. But you can actually make a tetrahedron yourself. This is your central atom. Mine's bigger than most. This is hydrogen. So I'm making, I'm making a square-ish kind of shape, right? If I wanted to make a tetrahedral, if I wanted these groups to be further from my feet, right, where would I put them? You put them like this, and they end up being further away, right? That's nice. You guys tired of sitting? That's really good.
Everybody get up and do a break.
No, no break.
Oh, great.
So this is the tetrahedral shape, right? The bond angle for tetrahedral geometry is 109.5 instead of 90. And so that's the indication that, hey, it's actually further away. The bond angle, the angle between the atoms is bigger, so the atoms at the end must be bigger away, further away from each other. So there's 3 angles you have to remember. Linear, 180, trigonal planar, 120, and tetrahedral, 109.5. Okay. Ammonia, okay, there's a table that summarizes all this, and we'll go over it. I just want to get you the pictures in your head, okay? Ammonia is different because it doesn't have an atom at every point. It has a lone pair over here. Now, with 4 groups, what we call its electron geometry, the electron geometry is dictated by this, 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 and this. Right? It's still tetrahedral because it has 4 electron groups. But its molecular geometry, what its shape, the molecule shape is, when we do the molecule shape, we don't include the lone pairs in what we see because you don't see the electrons. So this is the molecule shape. It's this shape minus the electrons. And the reason these are pushed down is because the pair of electron that is up here is pushing them down. This is known as a trigonal pyramid. There's actually a thing called a square pyramid too, and that looks like, I was telling the class this morning, it looks like the pyramids you see in Egypt. Right? It's got a square base and 1 point at the top. That's known as a square pyramid. This is known as a trigonal pyramid because instead of a square at the bottom and the peak, it has a triangle at the bottom and a peak. Okay? The angles that are in here are usually slightly less than 109.5 because of the lone pair that's at the top that tends to push everything down.
Is this going to be trying to bond with another hydrogen? Like
Yeah, it can. So, that's a good question. So, what is this lone pair going to do, right? It can do this. And then we draw it like this, a wedge and a hatch. That's to show it going back. And it has a positive charge. This is how ammonium ion gets formed. It picks up another hydrogen that sits on top of this lone pair. But because the hydrogen already has an electron, it has to get rid of the electron in order to form that bond. So that's why NH4 plus it gets formed.
Could be a hydrogen ion.
And neutral.
Yeah, it's forming it with actually a hydrogen ion in solution usually. That's how we get to it most of the time. But you can actually, it's kind of a cool gas phase reaction too. You can get ammonium chloride to form in the air, and then it precipitates out of the air as a solid.
If that hydrogen neutralizes one of the lone pairs, that what you said, does that make it a radical?
No. It gets, hydrogen has to not have the electron on it in order to do that. So it's usually a hydrogen ion when it does that. Okay, so here's the shape of water, okay? Water is, H2O. How many electron groups do you see? Oh, sorry. How many electron groups do you see around there? Well, there's the hydrogens, and then there's the lone pairs, right? So a total of 4. So its overall electron geometry is still tetrahedral. It looks like a tetrahedron, but instead of having atoms at the two of the corners, it has lone pairs. And when you get rid of those lone pairs, the molecule looks like it's bent. Okay? The bent shape, though, is maintained by the fact the lone pairs push the hydrogens down.
That's the two pairs on the oxygen.
Yeah, the 2 lone pairs on the oxygen. And because you have 2 lone pairs, and lone pairs have a lot of electron repulsion associated with them, this bond angle tends to get slightly smaller. Okay, the remaining bond angle. It's usually around 105 or 104.5. So this is what you have to know. And we'll go over this. You get practice with this in class. But this is the number of electron groups. And really all you have to pay attention to is this. This is the number of lone pairs. Because the electron groups is always the bonding groups plus the lone pairs. So there's none here, and then this is tetrahedral. There's 1 here. This is the trigonal pyramid. So we'll get some practice with that in lab. There's actually models if you want to build them and look at them. But that's just a slide right out of your book. Okay. Let's pick this problem. Let's see. We're going to predict the geometry of SO3 2-. Okay? So for SO3 2-, I'm going to start with S in the middle. I'll put 3 oxygens on it because it's SO3. There's 24 electrons plus 2, so that's 26. That's my valence electrons. My remaining electrons is 20. Okay? And so I have to distribute 10 pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, now what do I do? Well, I'm missing 1. Like that. There, 10. So I'm good. That's it. Everybody has an octet. Everybody's happy. It's an ion, so I need to write it in brackets. So I would write it like this. And then there's a lot of dots that you have to draw, so just fill in the oxygens with dots. Yeah, I did that a little fast, but that's it there. Okay? So we want to predict its geometry. Well, how many groups are on the sulfur in the middle? 1, 2, 3, 4, right? So I count. It doesn't matter if it's a double bond or single bond either. It just counts as a group if it's an atom. And so there's 4 on here, so this is tetrahedral. That's with 1 lone pair. So that means it's, if you go back to the chart, tetrahedral, right? One lone pair, it's a trigonal pyramid. Or you could just know that from the shape and know the shapes, but, you know, sometimes that doesn't work out so good. Okay. Skip over some of these. Oh, I don't have time to cover everything. I just want to cover a little bit more, okay? And then I'm going to cover through electronegativity. And then we'll have to leave some stuff for the next exam. So that means you'll have to know Lewis structures for 2 exams, but that's okay. All right, so oxygen and hydrogen atoms, right? This is the structure. There's this concept called electronegativity, okay? Well, there's a couple of them. Yeah. Electronegativity, but the concept of electronegativity, it's how strongly, okay, how strongly an atom attracts electrons in a bond. How strongly an atom attracts electrons in a bond. So, for example, the electronegativity of oxygen versus hydrogen, right? How strongly does oxygen attract the electrons, and how strongly does the hydrogen attract the electron? If the attraction is exactly the same, right, the electrons stay exactly between the two. So what that means is, if you think about charge, okay, when you pull the electrons to one side, you're also pulling charge to one side. So if oxygen attracts, and it turns out oxygen does, if oxygen attracts the electrons more strongly towards itself that are in this bond here, right, then what will happen is this side of the bond becomes negatively charged, and we use a delta sign like that. That's this lowercase Greek d, okay? Same thing is true on this side, that the oxygen attracts the electrons this way. And what you end up with is a positive charge on the left and a negative charge on the right. So this side becomes positive and this side becomes negative. Like that. And so on the top we have something like this. Now, we have this term, it's called dipole. So you know what a magnet is, right? What do we call the ends of a magnet? The poles of a magnet, right? It's also a dipole, but it's a magnetic dipole. This is an electric dipole. And all that means is you have a positive charge and a negative charge. So how do you determine, right, where the electrons will be attracted to? And this is the table that is important, although it's really hard to see. Up here we have fluorine, and here we have acetane. Here we have hydrogen, and here we have cesium, and we're ignoring the transition metals because they don't follow the trend really well. Okay? But who has the highest electronegativity, does it look like? Fluorine. And the trend generally goes from low on this side to high on this side, okay? And there's actual numbers in the trend. The scale at the bottom's not placed correctly, really, but here's 0.7 for all the way down here, and there's 4 for all the way up here. And Linus Pauling was the guy who originally said, hey, I'm going to make lithium 1, and I'm going to make fluorine 4, and I'm going to put everything on a scale from 1 to 4 and see how it works out. And this is what we were stuck with, okay, so this is Linus Pauling's electronegativity scale. If two things are bonded together and their electronegativity difference is bigger than about 0.5, we consider that bond to have been polarized or have a dipole. And if it's less than that, we consider it to be nonpolar, okay? So, know the trend for this, because I'm stopping the chapter early because I don't want to get into too much about this. Okay, know the trend for electronegativity. Look to see how you determine whether a bond is polar, ionic, or nonpolar, and then take only that far. Okay, don't look at molecular polarity. The oil mixes water is kind of the end of that. Okay, don't get into that stuff too much.
In chapter 10 still, right?
What? It's still chapter 10, but it's the very end of it, and the last bit of it really fits well actually with our stuff we do on solutions, so I may actually hold it off till all the way till we do solutions and stuff.